Hi everybody, welcome back to the stats section of the dyspepsia module. We're on lecture 3 of 3, so this is the final time you'll hear from me, although it's a 3-part lecture. So we're going to look through 3 different chunks of material today about trends. So we've dealt in the previous lecture with the idea of looking for differences and trying to test for those differences statistically, and today we're going to look for trends and test for those using something called regression. So I always struggle to illustrate what I mean when I'm talking about differences in trends, and to encapsulate my puzzlement at the whole concept of trends. You can see this image on screen of somebody dabbing. I don't really know what that is or why it happened. I just don't basically understand memes. But anyway, if we were in a lecture theatre, I might give you my best dab, but not today. So if I can get my slides to move on. Today's job then is to have a little bit of an introduction to the idea of looking for trends, and then we're going to focus in on a key statistical test that allows us to test for a trend called linear regression. And then towards the end of the lecture we're going to deal with a separate topic really, which is actually about measures of confidence. So you've probably heard of confidence intervals, maybe heard of the standard error, so we're going to have a look in some detail at those ideas because they're really important in terms of expressing our confidence in the kind of sample estimates that we generate from data, as we'll see later on. So the first part then is to focus in on linear regression. So we're going to look at this important statistical test, which actually helps to illustrate many of the ideas that we've already talked about in the previous lectures. So when you're looking for a trend in science, what that really means is you're looking for an association between 2 or more continuous variables. So on screen here we've got 2 hypothetical variables, 2 things that we've measured. So let's just, for example's sake, say concentrations of statins or dose of statins and blood cholesterol. They might be 2 things that we're interested in the association between. So we could look in patients at the amount of statins they're taking or the concentration of statins in their body and relate that to blood cholesterol, and we might or might not find some kind of negative trend, negative association. So this is a typical scenario in which we're looking for a trend, and obviously we want to be able to say something concrete about any trend that we might find. So plotting a scatter plot, as I've done here, is very useful in helping us to visualize the data, but it doesn't necessarily tell us whether we've got a real relationship or whether what we're looking at could just be the product of a chance event. So if you think about those dots on that graph, the question is really how likely are those dots to have arisen if we kind of threw darts at random at the screen so that the dots were put down in a random pattern. How often would we see that kind of apparent negative trend just by chance? And if it's a very rare event by chance, we would conclude from that it's probably not by chance, and in fact actually there's a real biological or chemical trend underpinning this relationship. And of course the way that we go through that thought process I've just described in a rigorous way is to apply statistics, and in particular a statistical test, which is what we're going to do now. So just like with all stats tests, as the ones you've already encountered, you need to start with a hypothesis, because we're going to generate a p-value, a probability, associated with a particular null hypothesis. So the null hypothesis is the one that says nothing interesting is going on. So for this scenario where we're looking at for a trend between 2 variables, I'm going to imagine that we have a 2-sided null hypothesis which says that there is no relationship between x and y, between the 2 variables that we've measured. If there's no relationship between x and y, there is neither a positive nor a negative relationship, then the null hypothesis actually can be expressed as an equation, simply as y equals a constant c. So what we mean here is that if there is really no relationship between x and y, then regardless of the values of x, y will average a particular value, let's call it c, plus or minus a bit of random noise. So that's the sort of boring null hypothesis that says nothing interesting is going on. And there is always a mutually exclusive alternative hypothesis to go with your null hypothesis. In this case, the alternative hypothesis, as we call it, is a familiar looking equation, hopefully, for many of you. You've probably encountered this equation at school. Y equals mx plus c is the equation of a straight line on a graph. a straight line between x and y, where m is the slope, so determines whether you've got a positive or a negative relationship, and c is the intercept. In other words, c is the value of y when x equals 0. So if this is statins versus blood cholesterol, what we're saying is, what would cholesterol be like in the absence of the drug? That's c. And then the mx bit tells you how, as you increase x, or the concentration of the drug, your blood cholesterol changes. Blood cholesterol being y in this case. So the alternative hypothesis here, expressed as an equation, but you can express it in words, which is that there is a trend with a slope m, which might be a positive or a negative slope, assuming we're adopting a two-tailed or two-sided hypothesis. You can have a one-sided hypothesis, in which case we would be making a specific prediction about whether this was a positive or a negative trend, but we're not going to do that for the purposes of this example. So to look at a real example, let's forget about statins for the time being and think about child poverty, actually. Child mortality and poverty. The reason I've chosen this example is because it introduces you to a wonderful website which is designed and motivated by people who are really interested in the public understanding of statistics and data. So the topics that we've been handling in these lectures, obviously in your case, are specific to your desire to develop a career in pharmacy, but for the wider public, as has probably been made particularly clear through the COVID crisis, understanding data and statistics is really important in all kinds of ways, not least in order to make sense of things that politicians tell you are true. So we're going to look at some data which are politically important, data comparing countries in terms of their wealth, their GDP, gross domestic product per capita, so in other words, how much money there is per person in a country, versus child mortality, so how likely you are to die before you reach the age of 5. And I've got a snapshot on the slide here from 2015, and I think you can see that there looks like there's a pretty clear negative relationship where each dot on this graph is a country and the size of the dot reflects the size of the country. So those really big dots, well, this huge red one here is actually China. So what I'm going to show you on Gapminder is that they have lots of lovely ways of visualizing these kinds of data sets and indeed showing you how things change over time. So I'm just going to come out of PowerPoint, and hopefully this will work. You should be able to see my web browser. So I've gone to gapminder.org, and they have a tool where you can graph all kinds of interesting data sets, and I've chosen to plot GDP per capita against child mortality. And this data set is continually updated, so we've already got last year's data, year before last data, 2019. And what I'm going to do is I'm going to play you an animation of what happens through time. So we're going to go back in time to 1960 and start watching how this graph changes. So each country is a blob here, and you can see them migrating around through time. Here's China, that enormous blob. And what you can see as a general pattern is there's a negative association here, it looks like, but there's also a drifting of these points down the graph. What does that mean? Well, that's actually good news because this is child mortality. So in general, for most countries, what we're seeing, and I'll just play that again, is a decline in child mortality, but much more so in some countries than in others. So look at the winners, these yellow blobs, for example, which are coming right down the graph to very low levels of child mortality. And this is on a log axis here, by the way, so the relationship is in a sense damped by the logging, but don't worry about that. The yellow blobs are the European countries. So I don't know which one of these is the UK. That's Russia there, for example, Italy, Germany, France. So European countries have, by global standards, relatively low child mortality, and one of the obvious reasons why we have low child mortality in Europe is that we are wealthy, very wealthy. Wealthy countries lead to well-educated people with good health care and all the other things that we might expect to drive child mortality. So in a sense, this is not a very surprising relationship, although at the moment we're only looking at the data. We haven't applied any kind of statistics, so we aren't sure that what we're seeing couldn't just be a chance event. I suppose the depressing part of this story is that the African countries, which are these blue blobs up here, are still way behind in terms of child mortality. Although, if we just once more play that animation, you can see that even in Africa, child mortality has improved during the second half of the 20th century, which is some reason to be cheerful, I guess. Okay, so do have a look at Gapminder. It's great fun to play around with data sets. There are data sets on everything from deadly serious things like child mortality to fun stuff, which I'll let you explore in your own time. But if we go back to our slides, I'm going to use this data set as an example of something where we might be looking for a trend. Perhaps we are, I don't know, the United Nations trying to make decisions about how best to tackle the problem of child mortality, and we want to understand whether or not wealth is really the key driver. So what we want to know from this kind of data set is whether the pattern that we're seeing on the slide could have happened by chance, or if it is genuinely likely to be driven by a real relationship. So we set up our hypotheses just as I explained. So just some basics here. X on the x-axis down here is GDP. It's actually the log of GDP, but you don't need to worry about that too much. So this is wealth per person, per capita in dollars, but transformed with a logarithm, so the numbers don't make a huge amount of sense. Basically 4 would be $1,000 per person in wealth generated per year. And on the y-axis, y is child mortality, expressed in the number of children dying before the age of 5 per 1,000 people in the population. So, you know, in general, modern human populations experience relatively low levels of child mortality, thankfully. And our null hypothesis here was that there is no relationship between child mortality and GDP, which expressed as an equation is y equals c, where c in this case is just the average child mortality of all countries. So I've replotted the data here, and the green line represents the average of the whole data set, assuming this null hypothesis assumes that there is no relationship between GDP and child mortality. So we have a flat line. Doesn't matter what your GDP is, your child mortality is going to be c plus or minus a bit of random noise. So the alternative hypothesis is actually, in the case of the kind of analysis we're going to be doing, the line of best fit through these data, the line that reflects any trend that might be present. So here it looks like there might be a negative trend, and so we fit a trend line through the data with the best possible combination of intercept and slope so that the line goes through the middle of the data set. And this represents our alternative hypothesis y equals mx plus c. In this case, C is a little bit tricky to see because C is the child mortality when GDP theoretically is 0. Now, of course, there is no country on Earth where GDP is 0, so it's a bit nonsensical. But if there was a country with 0 GDP, then we can extend this line of best fit to find out what the mathematical intercept of this curve is, and it's up here at sort of around about 3.5 or 4 on a log scale. So that's our intercept, and m is the slope, which in this case is going to be negative for the line of best fit, because as x goes up, the child mortality goes down. So this purple sort of thing here is to reflect us the idea that we can measure the slope of this line, and that will be our parameter m. So with these two parameters, we've defined our alternative hypothesis. But of course, at this stage, we don't know what these parameters are. We're just sort of sticking a line on a graph and saying, well, there is a line of best fit. Which brings us to the statistical test we're going to do, called linear regression, which actually allows us to fit that line of best fit, find out what m and c are, and then ask what the probability of the data set is under the null hypothesis. If the null hypothesis is unlikely to be true, then we're going to conclude that this line of best fit is more likely to be true. Excuse me. So, just as with all statistical tests, linear regression is going to involve calculating a test statistic. So for the t-test that we saw before, the test statistic was called t. For linear regression, the test statistic is called f. So we're going to calculate f, and that's going to allow us to produce a p-value for this regression. Now you can do this in Excel, and indeed in the workshops you will do this, the workshops in the other module. So this is just a screenshot from Excel to remind you that hopefully by the time you get to do this you will have successfully added the data analysis tool pack into your menu system in Excel, which will then allow you to click on data analysis and choose regression as the test that you want to do in order to test this kind of XY type data set. And here I've run the regression for you on the data set we're looking at and calculated C and M, which are plotted in the Excel output that you get down here. They're called coefficients, sometimes called parameters. The intercept C is handily called intercept. So in this case it's 3.39, which corresponds, if you think back to that previous graph, and as we'll see in a minute, roughly to what we'd expect. And this slope parameter is called x variable 1 for some reason in Excel. Not very helpful terminology, but you can see here that the estimate is negative, minus 0.626. That's the estimated slope of the relationship, if there is one. Of course, we also need to calculate a p-value, which we'll come to in a second. In fact, here we go. So, as I said, this is a stats test, so it's going to generate a statistic that represents the strength of the relationship that you can see. And then from that we can calculate a p-value. So in our case, f is 487, which I can tell you is a very big f value because this is actually a very clear relationship, and we've got a big data set, so we've got quite good statistical power. And the p-value, well, this is typical of the sort of output you get in Excel. Initially it doesn't make a lot of sense. This is the p-value here. It's labelled significance, which is a bit annoying, but it means p. And it's written in this very strange form, 4.346 e minus 52, and that actually means 4.346 times 10 raised to the power minus 52, or times by 1 over 52. So what that really means is 0.0000051 noughts and then the number 4. In other words, this is an extremely small p-value, much less than 0.001, which is typically the lowest threshold that we would ever consider when looking at a p-value. So in a scientific paper, you typically see this p-value probably abbreviated to be p is less than 0.001. It can never be exactly 0, but in this case it's fractionally above 0 and certainly very small. So what this is telling us is that our value of f is extremely unlikely, almost impossible, but not quite, if the null hypothesis is true. And the null hypothesis says there ain't no relationship between GDP and child mortality. So in this case we would actually conclude that it's so unlikely that the data would have arisen if the null hypothesis was true. The p-value is so small that this relationship instead must be significant. The null hypothesis must be wrong. So we reject the null hypothesis, conclude that it's not likely that child mortality has no relationship with GDP, and instead conclude that there is a significant relationship. So our alternative hypothesis is more likely to be correct. Child mortality is related to GDP. So let's go back to the data again, plotted on the graph here. We've concluded that this relationship is significant, but we can actually get the stats test to tell us more than that. We already know it's given us M and C, and that allows us to draw the line of best fit onto the graph, and Excel will do this for you automatically actually. If you ask it to add a trend line, it will add a regression line. Using this equation, child mortality is 3.39 minus 0.626 times GDP, and that's what gives you this white line of best fit here. So you can imagine if you extrapolate it back, you're going to end up with an intercept of about 3.4, and you've got this clear negative slope, negative relationship. Great, so we have concluded we have a significant relationship, and we can say exactly what that relationship is in terms of a slope and an intercept. The last question we might want to answer is, well, how strong is the relationship? Now, it's obvious from this data set that we have a pretty strong relationship. It's just a universal truth that poor countries have high child mortality and rich countries have low child mortality, with relatively little scatter. But we can quantify that scatter using another statistic called R-squared. And R-squared is a measure of fit of the line of best fit to the data. And it's a bit hard to imagine with the real data. So here are two simulated data sets with different R-squared values, even though they've got the same slope. So we've got exactly the same, or almost exactly the same line of best fit here, but we've got two very different data sets. On the left-hand side, we've got a relationship which is incredibly strong, so that almost all of the variation in child mortality is explained by GDP. There's very little scatter around the line of best fit, and the R value is nearly 1. So 1 would mean a perfect relationship, or 100% of the variation in child mortality being explained by GDP. An R of 0.95 means 95% of the variation in child mortality is explained by GDP. So that's one end of the spectrum. A much weaker relationship is shown on the right hand side, but with the same slope. So the same increase in GDP gives rise to the same average decline in child mortality, but this time there's a huge amount of scatter. So any individual country deviates from this relationship plus or minus quite a lot. So in this case we can say that R is 0.4. That means 40% of the variation in child mortality is explained by GDP. So the rest, the other 60% of the variation, must come from other sources. So a country is, for example, way above this line or way below this line for some other reason. And it might be, you know, I don't know, the political system they're using, or whether they've recently had an epidemic of a horrible disease, just to name an example. So R squared is really useful, and R squared is given in the Excel output as well. It's called R square, and here it is, 0.739. Sometimes you see it expressed as a percentage, which is a bit more intuitive. So 0.739, or 73.9% of the variation between countries in child mortality is explained by GDP. And that's roughly true in the real world. So it shows you that the strength of that relationship is really quite marked. Right, okay, so so far so good. We've done or shown you how a regression test works, what the kind of output means, so we can apply this in lots of different situations, but there's yet more things we can do with this approach. So we can actually make some predictions based on regression of what we will find in the future. So let's look at a different example this time. Imagine that we were looking at a study, and this is a I've made the data up, but it comes from a real study originally, looking at how blood alcohol declines after somebody's drunk alcohol over time as your body removes the alcohol from the blood. So what we're looking at is 50 minutes after somebody's drunk a can of beer. We've measured the blood alcohol content and we've watched how that's declined over the following 200 minutes. So it looks from the data like we've got a nice negative relationship. We can calculate the equation of that relationship. Blood alcohol equals 81.09 minus 0.2 times time. Once we have that relationship, we can then start to ask predictive questions. So we could say, well, if you go out and drink a can of beer, how much blood alcohol will you have left after 100 minutes or 200 minutes? Using this equation, we can say, on average, what we would expect a person to show in terms of blood alcohol after a particular time. So let's look at a couple of examples. We can ask sort of different versions of the same question. So we could say, like I say, what's the concentration of alcohol in the blood at 100 minutes? And we can plug 100 minutes into our equation. So blood alcohol equals this negative slope times 100 plus 81. Do the maths and you find that the answer is 56.91 milligrams per deciliter. So this person has, people on average in this study are expected to have 56 milligrams per deciliter of alcohol after 100 minutes. But you could say, well, how long until it's all gone? So this is flipping the question on its head in a sense. What you're saying is, at what point will blood alcohol concentration be 0? So we can say, when will y equal 0? Well, given everything else we know, the only unknown remaining is t. So if we know that we're looking for 0, we can rearrange this equation to find t, which in this case, if you do the maths, comes out at 335 minutes. So 335 minutes after the consumption of this beer, the blood alcohol has gone. Now, bear in mind, I did make this data set up based on a real study, so please don't go assuming that if you've drunk some alcohol that you're going to be completely sober after 335 minutes. I don't know whether that will be true. It probably depends on all kinds of factors, which we haven't looked at in this study. But the point is, if we do a regression, we get a line of best fit. We know the equation of that line. we can then use it to calculate what we would predict to happen in the same population if we collected more data. And that's really useful, and you can do it. You can calculate x based on y or y based on x. Both will work. So that's nearly the end of this regression topic. The last thing I want to say before the break is that when you look at the output in Excel, you see alongside all of the things we've already talked about, the F statistic and the p-value, the R squared, the slope and the intercept, we also see some standard errors and some confidence intervals. So in fact the intercept C and the slope parameter M both come with a standard error and some confidence intervals expressed as lower and upper 95% bounds. This is really common. Lots of stats that you see quoted, not just the stats that are produced by regression, but even something like a mean, for example, that you might see quoted, will come with some kind of confidence interval, a standard error, an error bar on a graph. All of these things are related and they're really important, and that is what we're going to talk about after the break.